things what. This is part 3 of a multi-episode series on wave particle duality. If you have not watched the first 2 episodes, I highly encourage you check it out. The link of it can be found in the description below. In this episode, we will talk about quantum superposition and what it means for the collapse of the wave function. So taking off where we left last, it's mid-1920s and 30s, and we're introduced to 3 new pioneers by the name of Erwin Schrödinger, Niels Bohr, and this guy, I really meant Werner Heisenberg. In my previous video, we have already established that in a double-slit experiment, photons create the interference pattern on the screen. Now, an extension to that experiment is if you want to cheat and observe which slit the photon actually traveled through. For this, we introduce a detector in the experiment, which would have to interact with the photon to determine which way the photon actually traveled, the top slit or the bottom slit. A very interesting outcome is observed when we do this. The interference pattern disappears, and what is left behind is a blob-like pattern, which would be typical in a particle-like behavior. Wait, how can this even be? In fact, if we leave the detector unplugged, the interference pattern reappears. And when we interact with the photon, the interference pattern disappears again. This effect is called the collapse of the wave function. One of the interpretations that I personally tend to agree most with is the Copenhagen interpretation, articulated by Bohr and Heisenberg. And it is based on the principle that wave-particle duality, that is, particles such as electrons and photons exhibit wave-like and particle-like properties. The uncertainty principle. This is basically saying that properties such as position and momentum cannot both be precisely known simultaneously. The more accurately you try to determine one, the less accurately you'll know about the other. The observer effect. This is basically the act of measurement or observing affects the system being observed. In the context of double slit, the act of observing which slit the particle goes through collapses the wave function and basically alters its behavior from a wave to a particle. The probabilistic nature, this is the outcome of measurements that are inherently probabilistic. Instead of predicting a definite outcome, quantum mechanics provides a probability of different outcomes. And lastly, the quantum superposition. So that is, before measuring, a particle can exist in superposition of states, meaning it exists in multiple states simultaneously. It's only when if a measurement is made, the system chooses which one these states are in. So, for example, in this experiment, the probabilistic nature and quantum superpositioning tells us that the photon might be in different positions, right, with some probability. It is only after we observe that the system needs to pick which position the photon is in. This quantum superpositioning leads us to Erwin Schrödinger's famous thought experiment, in which we have a cat that is inside a closed box. Inside the box is also a radioactive substance that has a 50% chance of decaying within the hour. In the case of decay, the detector in the box will deploy an apparatus that would break open the poison vial, causing the cat to die. Now, according to the principles of quantum superpositioning, the atom is said to be both in decay and non-decay state, which means the system containing the cat is also in a superposition of two states, one where the cat is alive, one where the cat is dead. The cat is theoretically both alive and dead at the same time. The act of opening the box and making observation is said to collapse the superpositioning, forcing the system into choosing one of two possible outcomes, which is the cat is alive or dead. Schrodinger's cat is often used to discuss the challenges and implication of interpreting quantum mechanics, especially the nature of superposition and the role of an observation in determining the reality at a more quantum level. Since then, there have been many other variations of the double-slit experiment that I will leave here for your reference, all of which aim to deepen our understanding of fundamental principles of quantum mechanics. They also explore the boundaries between classical Newtonian physics that we are more familiar with, objects with mass, and quantum behavior, where we get introduced to more probabilistic and indeterministic elements. The field of quantum mechanics continues to evolve, and researchers are continuously devising new experiments to push the boundaries of our knowledge. Until we learn more again next time, stay curious and tune in to All Things What.